Okay, here let's say you have a positive charge here and then another charge over here, and very often you will get a question where they will say, okay, suppose if I have a small charge kept over here, and if you are displacing it a little bit this way, suppose let's say I'm displacing it a little bit this way, what is going to happen is plus and plus will repel. So that means here it was in equilibrium, but here the force of repulsion because of this will be higher. The force of repulsion between this Q0 and Q will be less because of the distance, which means this force is more and it's going to push it this way. So it will try to bring it back to the original position, but it will overshoot here and it will do the same thing. So it will cause a SHM, simple harmonic motion. So remember, this is in the axial line. There is another concept called SHM in the equatorial line. So that we will see it separately. For now, we are going to see the SHM in the axial line. So I am going to call this as F1, this as F2. So F1 is going to be equal to, let's take this as L, and simply do the formula, apply the formula. So K Q naught by the distance square. So the distance is this distance. So L minus, let's say this, you are displaced it by distance of x. So this has to be L minus x, the whole square. F2 is same thing, K Q naught. It will be L plus x, this distance. So it will be L plus x, the whole square. So the F net force is F1 minus F2. So KQ, do the math yourself, 1 minus 1 by L minus x the whole square minus 1 by L plus x the whole square. So if you do the math, I think you will get something, L plus x the whole square minus L minus x the whole square, you will get 4Lx. You can do it, simple mathematics. And this is a plus b, a minus b the whole square. So I can write it as L squared minus x squared the whole square. Okay. And here F net I am going to call it as mass into acceleration. And we are talking about the restoring force. Restoring force you must have studied in simple harmonic motion. When you are displacing it on the left side, the force is trying to push it towards the right. So that means the displacement x and the acceleration will be in the opposite direction. Force and acceleration will be in the opposite direction. So we put a minus here. Okay, so this is a restoring force. That's all. So bring the m on this side. Generally, the usual cases, they will say that the x is very small compared to L. X is very small compared to L. So that means x can be ignored here, not here. So that means it will become a is equal to minus 1 by 4 pi epsilon naught q by 4L x. Let me write it separately. 4L divided by L power 4 by L power 4, because x goes away, x squared is very small. So if I cancel this, I should be getting L cube here. So you must have studied that A is equal to minus omega squared x. That's the characteristic equation of SHM. So in place of minus, you have minus. In place of acceleration, you have acceleration. In place of x, you have x. So in place of omega squared, you have this entire thing. So find out the omega, and then you can find the time period. So very often they'll ask you to find the omega, angular frequency omega, or the time period. So let's do that quickly. You can do it yourself, not very difficult. So omega is equal to 4 and 4 will cancel. So Q into Q, and very often I forget that the mass comes on this side, so I think divide by M. So Q by anything else here? Okay, so pi epsilon naught M. Then don't forget there is a square root. There is a L cube here. That's all I think. I hope I have not missed anything else. Okay. After that time period, very easy. So time period is 2 pi by omega. So 2 pi square root of this reciprocal. So pi epsilon naught m L cube divided by Q into Q. If you want, you can take this 2 pi inside, so it will become 4 pi squared. So it will become 4 pi cube epsilon naught ml cube. Okay, so that is left to you. Okay, thank you.